Continuing on from video 8, the annihilation and creation operators, let's look at this page, which is filled out with, I added some reds, it's got some color and different things like that. But let's go back to remembering what we're talking about. We're talking about the hydrogen molecule, minimal basis with 4 orbitals. And in those 4 orbitals are 2 electrons that balance out with the 2 protons. Okay, now you feel comfortable. Well, you won't feel comfortable for very long because this gets really involved. All of these terms are packaged up in this little piece right here, which seems strange. Well, I've got a creation operator and an annihilation operator, and then I have an index of P and Q and 0 to 3. Now what does that mean? Here are the possible combinations: 0, 1, 1, 0, 1, 1, 1, 2, 2, 1, 1, 3, 3, 1, 2, 3. So really there's a lot of combinations here. It's not just 4, it's how many do we have? Well, it's going to be the number of 2 electron combinations in 4 orbitals. And here's the 1, 2, 3, 4, 5, 6 combinations of those orbitals. We looked at this screen in the last video. Now these creation and annihilation operators, they need something to operate on. And they can operate on something very common, is the ground state for the hydrogen molecule, the symmetric ones. That's where these are the bonding orbitals where we got 2 electrons attracted to both protons kind of at the same time, and they form that bonding. Now, this doesn't have to be the starting point for this Hamiltonian, but I'm going to go ahead and choose it that way, just for our example of trying to work things out. So think of it as this being 0, 1, 2, and 3. So if this says, let's start off with the very first state of 0, 0. That says get rid of something at 0. Okay, there's the 0 state, so we get rid of that, and so that electron's gone. Then we put an electron in that spot. Okay, we put it right back in there. Well, what kind of nonsense is that? I created this page to prove to myself how this annihilation and creation operators really work when we apply it to all these different states. Now each one of these combinations is a P and a Q. So here's 0, 0 all the way to 3, 3. Okay, let's get started. And one thing I should stress is that we go from right to left here. We apply the annihilation operator first, or whichever operator is there, and then we go on to the next one there. So we go annihilation and creation. So this says annihilate something at position 0, which would be here. So we annihilate it, and that's what ends up. We got rid of that 1. Now we create 1 right there. Now we're right back to where we started. And this is not really a valid change. Really what we want to prove is that we're exciting 1 electron, or 1 electron moves once we apply these operators. So this one, nothing happens. And if we do the same thing with 1, 1, this is state 1, so you get rid of it and then you put it right back where it was. So I'm putting an X there to prove that that doesn't make sense. Now, what are these zeros all about? Well, let's look at this. This says annihilate electron 1 first. Okay, we annihilated it. Then what we're going to do is populate position 0. Well, position 0 is already populated, so that's an invalid operation, so it gives us a 0. So that knocks the whole thing out. Here we're trying to annihilate 2 and 3. Well, those aren't occupied, so if we try to get rid of them, it's going to return to 0. Same thing down here. 2 and 3 returns to 0. 2 and 3 returns to 0. 2 and 3 returns to 0. So that gets rid of a bunch of these. Now, what about if we try to populate 0 or 1? Let's see what happens there. Well, if we try to populate 0 or 1, that gives us a 0 out here. See, that gave us a 0 out there. And let's see, what are the other 0s and 1s? Where we're trying to populate 0s and 1s. Okay, well that's it. So we can populate 2 because that's not occupied. We can populate 3 because that's not occupied. But we have to find the magic combination where you get rid of 0 or 1 and populate it with 2 or 3. So here's 2 good combinations. Here's 2 good combinations. So out of all this mess, we only have 4 valid results. What you can think of is this builds the 1 electron excitation thing. Now you might think this is an awful lot of trouble to go through just to prove that you got these 4 states. But what if you have a lot more orbitals that you're dealing with? Then the whole thing gets a lot more complicated. Okay, we dealt with this item here, which takes 1 electron and moves it. Or we can call this electron hopping. And down here, we've got this repulsion term. And what happens in the repulsion term is we move 2 electrons at the same time. We get rid of 2 and we add 2. So we move electrons around in this fashion. So let's do a quick review of this one and see what the results are. Okay, in this scenario, here are the annihilation and here are the creation orbitals. And just as a review, here are the different orbitals that we can deal with. Now, if I was to list all of these combinations here, that would be 256 possibilities. But all I'm going to do is focus on the 24 that are non-zero. Now, the only 2 electrons that we can get rid of are in positions 0 and 1. So you'll notice all of these different rows have a 0 and 1 that's involved there. And as far as adding electrons, we can add electrons pretty much anywhere we want to, as long as we don't try and add the same electron in the same orbital. So those have been eliminated. So here's the non-zero possibilities that we come up with. We can return the same thing that we started with, or we can do something that the other one could not, and that's a 2 electron excitation, where we've got 2 electrons here and now they're up here. So here's the 1 electron excitations, which look similar to what we just talked about, and here's this other one that we add. But we always change 2 electrons at the same time when we create these. Now that we've determined how these operators work with basis states, now we need to find out what are these things, this H and this G. Here's the bad news. This is what the H is, which it combines all the information from up here, and this one, which combines all the information from up here. But the good news is there are standard computer algorithms that already can calculate this stuff. So when we're trying to figure out our molecular stuff, and set it up in a quantum computer, we don't have to really understand all this stuff. Now, I toiled over a way to describe this, and let's call it this way. These provide molecular orbital specific calculations, and those produce necessary constants that determine how electrons move and interact with orbitals. So without these constants up here, we won't really know what the total effect is. Now I hope that's enough, because that's where I'm going to close off this video. Now the good news is this second quantization sets us up for quantum computing and converting all these things to qubits. So that's where we're headed next. Well, into the computing area.